Hello everybody, very good evening. Welcome back again. In the last class we have discussed about the RRB JE revision series along with PYQs for electrical engineering students for the subject power systems, right. So, in the last class, we have started our discussion on transmission and distribution of electrical energy, and we have seen some concepts of the transmission and distribution, and we have discussed some questions also. And students also involved in the discussion, and we have clarified the doubts in the class also, right students. Now, we are going to discuss some concepts of fault analysis and some concepts of power system protection and some questions also along with them, right students. So, as we have discussed already, so this is the revision series along with the PYQs for electrical engineering students. So, started on 7th yesterday, and it will be continuously on every day from 7 p.m. right. So, students you can attend the classes and you can clarify your doubts related to your subjects, right. So, next thing, myself Prasad DMV, so we are going to discuss the next topics of power systems here, right students. The fault analysis, the next topic we can discuss here. So, in the fault analysis, so what are the various types of faults we are having? The various types of faults we are having are, we can say, first one is open circuit faults, or these are also called as series faults, and second one are short circuit faults, or these are also called as the shunt faults, right students. So, there are two types of open circuit faults. One is one conductor open circuit fault and two conductor open circuit faults. So, we can say here, so in case of open circuit faults, we are having two types. One is one conductor open fault, So, means whenever we are having a power system network like this, suppose if this is the power system network, we are having network 1 which is connected to one more network here. So, this is one more network 2, and these two networks are connected by three transmission lines. So, this is A phase wire, this is B phase wire, and this will be the C phase wire. If any fault occurred in any one of the line, if one conductor got open circuited, suppose if one conductor got open circuited, then that fault is called as the one conductor open fault. This is one conductor open fault. So, here the current will be there in phase A, IA will be there, the current will be there in phase B, IB is also there, but the current in phase C, IC will be is equivalent to 0. Alright students, that is one conductor open fault. Coming to the next one, two conductors open fault. Right. Similarly, we are having the networks connected here. This is network 1, this is network 2, network 1 and network 2, and these two are connected by three lines A, B and C. So, this is A, B and C lines we are having. If any two conductors got open circuited, right. So, now these two conductors are got open circuited here. The current will be there in phase A, IA, but current in phase B, IB is equivalent to 0, current in phase C, IC is also is equivalent to 0. So, these two are called as the open circuit faults. Sir, if what happens if all the three conductors are open? If all the three conductors are open, we cannot say that as a fault, we can say that is a no load condition. Suppose, sir, if you are having a condition like this, this is network 1, this is network 2, this is network 1 and this is network 2. So, here all the three conductors are got opened. Then can we call this as a fault? Means no, this is not a fault, this is open circuit condition. Here IA is equivalent to 0, here IB is equivalent to 0, here IC is equivalent to 0. This is called as a open circuit condition. Right students, these are the three types of open circuit faults. So in case of open circuit faults, we can say the voltage will be very high in open circuit condition. In open circuit condition, the voltage increases, current decreases, means low current will be there, right? High voltage and low current operation will be there, and we can say no active power flow, will be there, and the generator speed will be increased, speed of generator increases. As a result, frequency of the system increases. So this is the characteristic of the open circuit fault, right? So you can characterize the open circuit fault like this: low voltage, high voltage, low current, no active power flow, and high speed and high frequency. Like that we can characterize the open circuit fault. Similarly, coming to the short circuit faults. So here, suppose students, if you are having a 3-phase synchronous generator, if this is the 3-phase synchronous generator which is having 3 terminals, this is phase A terminal, this is phase B terminal, and this is phase C terminal, where this is A phase, B phase and C phase. If you got a fault in any one phase, suppose you got one fault here, clear, right? So one fault has been grounded. Now under this condition, only that phase voltage VC will become 0. Now this is called as, this type of fault we can call it as single line to ground fault. Simply we can say LG fault. It is an unbalanced fault. Why? Because so only 2 phases are having the loads. Maybe suppose if the system is under loaded condition, suppose if the system is under no loaded condition, so A phase current, B phase current will become 0, only C phase current will be existed. In any case, it may be under loaded condition or it may be under no load condition. So all the 3 phases are not having equal currents, all the 3 phases are not having equal voltages. Got it, right? That's why it is called as a unbalanced fault. So that LG fault is an unbalanced fault. That is the first type of fault. Single line to ground fault. And one more type of fault we can take here. Suppose if this is the generator, these are the 3 phases, A phase, B phase and C phases, A, B and C. Under this condition, if the fault occurred between any 2 phases. Now here also these 2 phases are having same current, the other phase is having the different current, right? So this type of fault is called as double line fault. It is also unbalanced fault. So single line to ground fault is also unbalanced fault. So this is also double line fault. Here the values of VB and the values of VC are exactly same. VB is exactly equivalent to VC, but it is not equivalent to 0. Why? Because whenever fault is grounded, then only the ground potential will be, suppose if this is 0 volts, this 0 volts will be appearing on this point whenever it is grounded. But this is not grounded, that's why the ground potential is not going to appear on the line. Got it right, students? So single line to ground fault is unbalanced fault and double line fault is also unbalanced fault. And one more fault you can discuss here. Third type of short circuit fault. These are the 3 phases, phase A, phase B and phase C. Phase A phase, B phase and C phase. Now, if B phase and C phase are grounded, short circuited and grounded, under this condition the value of VB is equivalent to 0, the value of VC is also is equivalent to 0. Why? Because the ground potential is going to appear on the lines. Now, only two phase voltages are 0, the other phase voltage is not is equivalent to 0. It is also an unbalanced fault. Now, this is called as double line to ground fault. Double line to ground fault. So, this type of fault. Clear, right? So, these are the three types of the unbalanced faults. And one more fault you can discuss here, the fourth type of fault. There are three phases, A phase, B phase and C phases, A phase, B phase and C phases. Now, all the three lines got short circuited. All the three lines got short circuited. Now, the current flowing in phase A, the current flowing in phase B, the current flowing in phase C, the magnitudes are same. They are having equal magnitudes and a phase angle difference of 120. Right? This type of fault is called as the balanced fault. Balanced fault. So, this is called as three phase fault or triple line fault. Triple line fault or three phase fault. Three phase fault. But it is a balanced fault. It is a balanced fault. Right. And one more fault we can take here. One more fault. The fifth type of fault. These are the three phases, A phase, B phase and C phase. A phase, B phase and C phase. Now, all the three phases got short circuited and then grounded. Now, the ground potential will be appearing here. Now, here VA is equivalent to 0, here VB is equivalent to 0, here VC is equivalent to 0. So, all the three phases voltage will become 0. Now, under this condition, the current flowing through phase A and current flowing through phase B, the current flowing through phase C, all are having equal magnitudes with a 120 degree phase angle difference. That is why it is also called as a balanced type of fault. It is triple line to ground fault. This type of fault we can call it as triple line to ground fault. Triple line to ground fault. It is also a balanced fault. So, totally 5 types of faults in short circuit faults we can say. So, what are those? We can write here the types of the short circuit faults. Types of short circuit faults. Short circuit faults. Here, first one is LG, line to ground, that is single line to ground. Second one is double line, that is line to line. Third one is double line to ground, LLG. Fourth one is triple line fault, triple L. Fifth one is triple line to ground, triple LG. Here, the first three, these three are called as unbalanced faults, or we can say unsymmetrical faults. Unsymmetrical faults, right? And these two, triple L and triple LG, these two are called as balanced faults or symmetrical faults. Symmetrical faults. Remember students, whenever all the three phases are involved in the fault, it may be all the three phases open circuited, it may be all the three phases short circuited. The system always lies in balanced condition only. You can check here. So, here whenever all the three phases are open circuited, that system is under balanced condition. Whenever all the three phases are short circuited, here also the system is under balanced condition. Right students, that you have to remember. So, these are the various types of the faults. So, here based on the location of the fault, whenever fault occurs at the far end of the transmission line, here we are having the load, Here we are having the load. Whenever fault occurs here at this point, we can say here triple L faults, that is triple L and triple LG faults. Simply we can say 3-phase faults. 3-phase faults are the more severe faults and LG fault is the least severe fault. We can say here at this point 3-phase faults are more severe and LG fault is least severe fault. And whenever fault occurs at the terminals of the generator, right, we can say fault at the terminals of generator at this location. Here LG fault will become the most severe fault. LG fault is the most severe fault and 3-phase fault is the least severe fault. That you have to remember. These are the previous questions. Generalized statements are, they are not giving the location of the fault. They have not given fault at the generator terminal or fault at the load side. They have not given any statement. Generally, the highest priority of fault location is at the load side. At the generator side, you cannot get the faults. Generator is the element which is least affected by the faults. Generator is always located in a closed casing, right? But transmission lines and the transmission towers, substations, all those are in the open area, so that there is chance that we are having more type of faults. Got it right, students? So the generalized statement is this one, generally. So what we can say, generally 3-phase fault is the most severe fault, LG fault is the least severe fault, right, students? And 3-phase fault is the least common fault. It cannot occur that much easily, but LG fault is the most common fault. We can say here, we can say LG fault is the least severe fault, and most common fault, frequently occurring fault is the LG fault. And similarly, triple L fault and triple LG, we can say 3-phase faults. 3-phase faults are the most severe faults, and least common faults. Right, students? This is the somewhat clarity about the faults. And how can I characterize the short circuit fault? So you can see the characteristic of the short circuit fault, right? In case of short circuit, short circuit fault. Students, in case of the short circuit fault, we can say here the voltage will be very low. It may become 0 nearly sometimes may not be 0, that depends upon the fault impedance between. Suppose if the line is directly grounded, that is a dead short circuit fault called as bolted fault. So remember, students, bolted fault means dead short circuit fault, so that voltage will become 0. Suppose in between, if you are having any impedance, suppose if a tree is falling on a line, tree impedance you have to consider, right, students? So at that condition, the ground potential will not appear on the line, right? So here we can say high current operation will be there, low voltage operation, and less active power flow, and high reactive power flow. high reactive power flow. Sir, what happens in open circuit? We have not discussed about reactive power, means their load is disconnected. Here system is grounded. System is grounded here. The system is under still active condition only. Why? Because a short circuit is there. Under short circuit condition, we are unable to transfer any amount of active power, but still the current is flowing through the line. Why? Because of the short circuit is there, that current is transferring a huge amount of reactive power to the fault point. So that because of high reactive power flow, the power factor of the system will become very low, low power factor. Low power factor. So how much you can say it is ZPF, zero power factor lag approximately. So approximate power factor, not exact, approximate power factor will be zero power factor lagging condition, right? And so low speed of generator and low frequency, and also system will become unbalanced. In case of open circuit and short circuit, in both the cases system will be unbalanced. That also you can add. Got it, right? Unbalanced condition, unbalanced operation also will be there. So this is the characteristic of the short circuit fault, students, right? Now, so what are the various formulas in case of LG, LL, triple and triple LG condition? So we have to learn some formulas. I will write those formulas, students. So we will take different types of faults here. LG fault, LL, LLG, triple L and triple LG faults. What are the sequence currents, sequence voltage, positive sequence currents, fault current and subtransient impedance values. See, to analyze the unbalanced system, we have to use the symmetrical components. So positive sequence, negative sequence and zero sequence components we have to use to analyze the unbalanced system. So in case of LG fault, the sequence currents, we can say all are same. We can say here IA naught is equivalent to IA1 is equivalent to IA2, all are same in case of the LG fault. Sequence voltage sum will be 0, VA naught plus VA1 plus VA2, the sum is equivalent to 0. The positive sequence current IA1 we can write here, the positive sequence current IA1, where the value of IA1 is equivalent to EA1 divided by Z1 plus Z2 plus Z0 plus 3Zn, and if the fault impedance is there, you can add that fault impedance also as 3 times of ZF, right? You can write plus 3 times of ZF, right? That is the fault impedance. If there is no fault impedance, substitute this is equivalent to 0. If there is no neutral impedance, substitute this is equivalent to 0. And the fault current IF is equivalent to, the fault current will be IF, we can write here. This is the fault current we can take. The value of the fault current will be 3 times of IA1 or 3 times of IA2 or 3 times of IA0. Why? Because all are same. We have taken IA0 is equivalent to IA1 is equivalent to IA2, all are same. Where the denominator of the positive sequence current is called as the subtransient impedance. What is that? Z1 plus Z2 plus Z0 plus 3Zn plus 3Zf. That is called as the subtransient impedance for the LG fault, right? Students, if you are having any doubts, please clarify doubts. Let me check who are attending the class. Right. Students, if you are having any doubts, please clarify doubts. So that's about the right. Good evening, Raju. JE preparation 25. Good evening. Right. Now see the next type of fault, line to line fault. In case of the line to line fault, the current conditions, sequence current conditions are IA0 will become 0, but whereas IA1 is the negative of IA2. IA1 is the negative of IA2. and sequence voltage conditions where VA naught is equivalent to 0 and VA1 is exactly equivalent to VA2, that is the sequence voltage condition. And the positive sequence current will be EA1 divided by Z1 plus Z2 plus ZF, that is the positive sequence current, whereas the fault current will be root 3 times of EA1 divided by Z1 plus Z2 plus ZF, that is the fault current value. Subtransient impedance is same as the denominator, that is Z1 plus Z2 plus ZF, right. That is about the LL fault. In case of LLG fault, the current conditions will be sum of the currents IA0 plus IA1 plus IA2 is equivalent to 0, that is the current condition. Voltage conditions, it will be in case of the voltage condition, VA1 is exactly equivalent to VA2 is exactly equivalent to VA0. All the sequence voltages are same in case of LLG fault. And the positive sequence current will be EA1 divided by Z1 plus Z2 parallel to Z0 plus 3ZN plus 3ZF. That is the value of the positive sequence current. And whereas the fault current will be 3 times of IA0 is the positive sequence current. So, subtransient impedance will be same Z1 plus Z2 parallel to Z0 plus 3ZN plus 3ZF, like that we can add, right students. And coming to the triple L and triple LG faults, in both the cases all calculations are same only. In case of triple L fault, we can say the sequence current conditions will be IA0 is equivalent to 0, IA2 is equivalent to 0, only we are having IA1 which is IA. As it is a balanced fault, in balanced fault only positive sequence components will be existed, there are no negative sequence, there are no zero sequence components existed. And sequence voltage all are 0, VA0 is equivalent to VA1 is equivalent to VA2, all are is equivalent to 0. Every component will become 0. There is one previous question we are having, for which of the following faults positive sequence voltage component will become 0? You can check here. So, where VA1 is equivalent to 0, here VA1 is not 0, here VA1 not 0, here VA1 is not 0. The only fault where positive sequence voltage is 0 is the triple L fault. So, that triple L and triple LG faults we are having the same calculations. And the positive sequence current, it will be EA1 divided by Z1 plus ZF, here also same. Here the fault current will be same, EA1 divided by Z1 plus ZF, that is the fault current value, and subtransient impedance is Z1 plus ZF. So, all the calculations are same for triple LG fault also. Students, this table you have to remember. Actually, you have to see the derivations, how you got all these formulas. So, then only it is very easy to remember. So, when you do not have time, so at least after completion of the preparation, so make a table like this. So, try to write all these things, and along with this you can draw the sequence networks also for each and every fault, right. That will give you the complete fault analysis, right students. Now, so that is something about the fault analysis, students. So, why? Because we are having somewhat less questions related to the fault analysis in the RRB JE examination, that is why. So, we are going to the next topic here, that is power system protection, right. So, now we will go for power system protection here, power system protection. So, see students, you can expect more number of questions from power system protection, right. First of all, what are the various elements in power system protection? What is power system protection? Why we have to give the protection to the system? The need of this switchgear and protection system is that it has to continuously monitor, the entire power system network, and it has to ensure that there is no physical damage for any element from any abnormal condition. The abnormal conditions may be the faults, the abnormal conditions may be any overloading condition, any underload condition, any lightning surges or any switching surges, whatever it may be. The protection system has to ensure that there is no physical damage for the power system elements. What are power system elements? Power system elements means generators, transformers, transmission lines and the loads. Any element should never be damaged. That is the need, that is the duty of the power system protection equipment. Right, students? So, in this, what are the various elements you can say? The first element that you are going to discuss, here it is, the lightning arrestor, or it is also called as the surge diverter. What is that? It is the first equipment or last equipment of the substation, we can say. And what is the duty of this lightning arrestor? Means it conducts high voltage surges to the ground, right. So, whenever you are having an element like this, suppose if you are having an element here, if this element may be a transformer, across with this one we are connecting the lightning arrestor. So, this is the lightning arrestor. Here these two should be grounded. So, this total portion we are calling it as the lightning arrestor or surge diverter. And inside the substation, it always placed close to the transformer. So, wherever we are having the transformer, so close to the transformer, here we can place one lightning arrestor, here we can place one lightning arrestor. So, majorly it is protecting the transformer in the substation, right. And one more element is there, that is surge absorber. Surge absorber. Surge absorber will not conduct high voltage surge to the ground. It will absorb some value of surge and it will reduce the steepness of the surges. See, whenever a surge is grounded through the element, that is called as the lightning arrestor. But whenever surge is not grounded, but still the impact of the surge we can reduce, that is called as the surge absorber. There are various types of surge absorbers. So, capacitor type and inductor and resistor type and Ferranti surge absorbers. Right, student? That is the next element we can discuss. And the next element is wave trap or the line trap unit. So, actually students, listen carefully. Actually, in substation, we are trying to do the communication. So, with a load dispatch center. So, from one substation to the other substation, whenever we are trying to communicate, so along with PLCC kits, right, what is that, you can say power line carrier communication we are saying, right. So, whenever you are using that communication signals, the communication signal frequency will be very high, it may be in megahertz, sometimes gigahertz also. So, as the frequency is very high, the time will be very less, so that they can run very faster. So, these high frequencies are running very fast and meeting the some of the equipments of the substation, and they may damage the substation equipments, high frequency signals. That is why, to avoid that damage of high frequency signals, the element that you are going to use is the wave trap unit. It is going to filter out high frequency signals and it will allow normally power frequency signals. What we can say? The wave trap unit or the line trap unit will allow power frequencies normally, it won't allow the high frequency or carrier frequency signals easily. To filter out them, we are using the line trap unit or wave trap unit. Got it right, students? That is the purpose of the line trap. Simply we can say the line trap unit provides high impedance path for carrier frequencies, low impedance path for the power frequencies. Low impedance path for power frequencies, high impedance path for carrier frequencies, that you can remember, right. And one more element is isolator. So, what is the purpose of isolator, students? The purpose of isolator is to maintain the circuit breaker. So, actually the isolator always operates under no load condition. It always operates under, it always operates under no load condition. No load condition. So, you may be having a doubt, sir, under no load means already current is 0. When current is 0, what is the need to operate a switch? Isolator is also a series switch. So, why, what is the need to open the switch means for maintenance of the circuit breaker, right. So, not only the isolator, one more element is there, that is the earthing switch or the earth switch. it is also used for the maintenance of the circuit breaker, right. So, you can see the sequence, clearly here. For opening a circuit, what is the sequence you can follow? The sequence that you can follow for opening a circuit, first one is open circuit breaker first of all, later on close the isolator, open the isolator and then close the earth switch. Clear, right? Opening a circuit means before maintenance of circuit breaker. Right? And similarly, for closing a circuit, whenever you are closing the circuit, means after maintenance of circuit breaker. Students, after the maintenance, the first duty is open the earth switch. Second one is close isolator, and third one is close the circuit breaker. They are the sequence of operations you can do. Right, students? Next one, current transformer. The most important equipment is the current transformer CT. So, we can say it is used to step down high value of primary currents to very low value of the secondary currents. So, it is stepping down the currents, not the voltage. But students, you can understand here, step up transformer and step down transformer, you have given the name based on the voltage, not based on the current. Clear, right? It is stepping down the current, means it is stepping up the voltage. Got it, right? So, that we can say current transformer is a step up transformer, it is not a step down transformer. It is stepping down the current, but it is acting as a step up transformer. Clear, right? And it is used to measure the current and give the trip signal to the circuit breaker. So, current transformer is acting as the relay circuit, right. And the rated secondary current we are having are 1 ampere CT and 5 ampere CTs. We can say it is a step up transformer. We can say the CT ratio is CT primary current divided by CT secondary current. And there are two types of CTs we are having, one is for measuring purpose, one is for protecting purpose. So, the CT which we are using for protecting purpose, that we are calling it as the relay, right. So, whenever you are using CT as the relay, right, so that relay is always set for minimum fault current, right. We can say the relay is always set for minimum fault current, as it has to sense all the types of faults, right. So, LG fault, LL, triple LG, it has to sense all the types of faults, that is why it is setting for minimum fault current. Suppose if the LG fault current is 10 amperes, LL is 15, LLG is 20, like that we are having the currents in sequence, right. Suppose if the relay whenever it is operating for 11 amperes, automatically it can operate for 15, 20, 25, 30, like that. That is why set the relay always for the minimum fault current, right. And the circuit breaker is always set for maximum fault current. maximum fault current. Right students? Sir, what you are saying, relay is sensing the fault, relay is giving the trip signal to the circuit breaker and circuit breaker will trip the circuit. Relay is sensing the minimum fault current, right? Whenever relay is sensing minimum fault current, immediately circuit breaker is going to be operated. How can you say circuit breaker will operate for maximum fault current? The meaning setting is, see students, circuit breaker has to open the contacts. Open the contacts. Whenever contacts are open, you are going to experience a arc between the contacts. Got it right? That arc will damage the circuit breaker contacts. That's why this arc should be minimized. This arc should be minimized so that I need to increase the distance between the circuit breaker contacts. So that I need to place the largest distance where the circuit breaker will never be damaged. That largest distance will be decided by the largest fault current. That's why circuit breaker is always set for maximum fault current, relay is always set for minimum fault current. Right students? Right. And the next element is, so current transformer, this is the current transformer we are having in the grid location. Next one is potential transformer, same as that of the current transformer. The potential transformer, we can say it is stepping down the voltage so that it is a step down transformer. So the rated secondary voltage, so generally we are having is 110 volts. So we are having measuring type of PT and protecting type of PT also. Protecting type of PT we can use it as the over voltage relay, right? We will see some questions here. Students, you have to give the answers. Which portion of the power system is least prone to faults? Any answer? Which portion of power system is least prone to faults? Option A, alternators. Option B, switchgear, transformers and overhead lines. Very good Balaji, perfect. Right. So as already discussed, the generator or the alternators are always least prone to the faults. Alternators are always least prone to the faults, right. The line trap unit employed in carrier current relays offers high impedance to 50 Hz power frequency signals, offers high impedance to carrier frequency signals, offers low impedance to carrier frequency signals and acts as protective device. What is the answer? What is the answer for this question? The line trap unit employed in carrier current relaying. Someone given it is option D, Narmos. Option C, JE Prep 25. Please check it. The line trap unit we are going to use to filter out the carrier frequency signals, right? They offers high impedance path for carrier frequencies, low impedance path for power frequencies. They offers low impedance to power frequencies, high impedance to carrier frequencies. Check the option. Give the answers perfectly. They offers high impedance to carrier frequencies and low impedance to power frequencies. What is the correct answer? Offers high impedance to carrier frequency signals. It is option B. It is option B. It's not C or D. Right. The fault clearing time of a circuit breaker is usually, students, generally the circuit breaker fault clearing time we cannot mention in seconds, right. So always we will try to mention in cycles of the supply voltage. It is always mentioned in the few cycles of supply voltage. So actually the circuit breaker operating time, CB operating time is divided into two parts. One is CB opening time, CB opening time plus arcing time, arcing time. There are two times. Here, for example, whenever we are saying SF6 circuit breaker, right, it is a 1.5 cycle circuit breaker, 1.5 cycle circuit breaker. See, whenever we are saying 1.5 cycle circuit breaker, it is having an opening time of, it is having CB opening time of 1.5 cycle, 1.5 cycle. Students, for 50 Hz system, for 50 Hz system, time for one cycle, for one cycle, time for one cycle, the time is 20 milliseconds. Time for half cycle, the time is 10 milliseconds. Whenever you are saying 1.5 cycle, the time will be 20 plus 10, that will be 30 millisecond. Means the CB opening time will be 30 millisecond whenever we are saying 1.5 cycle circuit breaker. Generally we will mention 1.5 cycle circuit breaker like that. So, the CB opening time. Along with that, some arcing time will be there, it will be less than that of opening time. So, highest amount of time will be opening time, least amount of time will be arcing time. Suppose if it is 30 millisecond, it will be some 10 millisecond, then the CB operating time will be nearly 40 millisecond. So, that CB operating time is 2 cycles, it is a 2 cycle circuit breaker, right. The CB is having a operating time of 2 cycles, like that you can mention. That is why the fault clearing time of circuit breaker is always mentioned in few cycles of the supply voltage. Got it right? Right. Lightning arrestor should be located away from the circuit breaker, near the circuit breaker, near the transformer, away from the transformer. What should be the answer? Very good, Balaji. The lightning arrestor should be located. The lightning arrestor should always be located near the transformer, inside the substation, inside the substation. Got it right? Next one. Which of the following correctly represents the sequence of operations of isolator, circuit breaker and earthing switch while opening a circuit, while opening a circuit. So, for opening of the circuit, what are the sequence of operations you have to follow? See them? They have given the options: open circuit breaker, open isolator, close earthing switch, open isolator, close circuit breaker, open earthing switch, close earthing switch, open circuit breaker, open isolator, like that they have given the options. So, what is the perfect answer? What is the perfect answer here? So, Balaji given it is option A. What about JE prep and remaining students? Remaining students, you have to respond faster. So, already discussed here. Whenever we are opening the circuit, whenever for opening operation. So, first of all, open circuit breaker, open isolator and close the earth switch, close the earth switch. That should be the answer. So, open circuit breaker, open isolator and close the earthing switch. That is what we have discussed already. That is option A. Perfect, perfect, Balaji. Right, that is about the introduction part of power system protection. So, now we will see the classification of the relays, various classification. So, students, you can get questions, so maximum from this part, right, classification only, right, you can expect the questions from this part. Based on construction, we are having electromagnetic relays, thermal relays, solid state relays and physical relays, right. So, the most important part is electromagnetic type of relays, electromagnetic type of relays. So, the electromagnetic type of relays we are having, they can be used for protection for over current operation, over voltage operation, right. For directional problem also we can use the electromagnetic type of relays. And whereas thermal relays, what is the purpose of thermal relays? So, whenever overheat is there, right. So, the thermal relays we are having are thermocouple, and also bimetallic strip, they are the thermal relays we are having. And solid state relays are the we can say semiconductor based relays, they are the static relays, right. Physical relays are gas operated relays, right students. And based on operating quantity or based on the application, we can say over current relays, over voltage relays, under voltage relays, directional relays, distance relays and differential relays. So, we can say the under voltage relays are used for protection of motors, and directional relays used for protection of transmission lines. So, feeders, parallel feeders, protection of parallel feeders. So, over current relays, there are lot of applications, protection of generator, transformer, transmission line, almost all from external faults, over voltage relays, protection of alternator, right. And distance relays, protection of transmission lines, differential relays, protection of transformer, alternator and bus bar, right. They are the applications, right students. Now, what are various types of electromagnetic relays? So, see, electromagnetic attraction type of relays, electromagnetic induction type of relays. There are two types of relays, one is electromagnetic attraction type, electromagnetic induction type. In attraction type, so we can say the attraction type are used only for DC, applications, and these are used only for AC applications, right. Actually, attraction type of relays can be used for AC also, but so there is some problem whenever you are using for AC applications because of the torque which is produced in electromagnetic attraction type of relays for AC applications, which is pulsating in nature. Because of that pulsating torque, the relay contacts may be damaged. So, to avoid that problem, so normally we cannot use it for AC applications, but we can use, but we are not preferring that one. But here induction principle, definitely we have to use it for AC applications only, never use it for DC applications, right. So, here we are having induction disc type and induction cup type of relays. In induction disc type, split phase type of relay, watt-hour meter type of relays we are having. Students, in case of this, one point you can expect here is balanced beam type used to design impedance relays. In the distance type of relays, so the three types of distance relays we are having are impedance relay, reactance relay and Moore relay. So, in that impedance relay can be designed by balanced beam type of structure. So here split phase type are used to design over current or over voltage release. Over current or over voltage release. Whatever meter type and the induction cup type of relays, both are used to design directional relays. Right, students? These are the applications of various constructions. So whenever you are writing this, so default you have try to remember them. Clear, students? In case of differential relays, we are having two types based on current. So current differential relay, based on voltage differential relay. Right? So based on current, the applications are protection of transformer, alternator and bus bar. Based on voltage, we are having trans relay used for protection of feeders. So protection of parallel feeders, we can say directional relays. Protection of feeders, we can write trans relay. They are the various types of relays. Now you can see some questions here. Try to give me the answers. The first question: Buchholz relay is used in. Very simple question. Most famous question. So Buchholz relay. What is a Buchholz relay? Gas operated relay. We can say it is one of the physical relay. We have seen in the physical relays based on construction, that is gas operated relay. Where it is located? See, if this is the transformer main tank, on the transformer main tank we will be having a pipe. Which is connected to the conservator tank, right? So here we are going to place the relay. This is the conservator tank. So here we are placing the relay. So I will denote this one like this. This is the Buchholz relay. So there is one more question: where Buchholz relay is located? So it is located on the top of the transformer main tank. Connected between main tank and conservator tank. Right? So whatever the gas, right, it is producing the bubbles, the gas bubbles which are entering into the relay. So those gas bubbles are going to give the operation of the relay. For small faults called as incipient faults, right, it will give the alarm signal. For large type of faults like LG, LLG like that, so it will give the trip signal, right. So every time it is used for protection of transformer. So we can say the perfect answer is transformer protection, right. Next question: fuse. About the fuse. HRC fuses on a transformer provide protection against. The fuse wire is giving the protection against which type of fault? It is insulation failure, internal faults, external faults, low oil level. What is the answer? Any answer here? Insulation failure or internal faults, external faults, low oil level. Internal fault. Balaji, internal fault. Which relay is used for internal fault protection of transformer? See clearly, students, types of faults in transformer. First one is incipient faults. Incipient faults means, sir, what are incipient faults means? We can say oil leakage is one of the type of incipient fault, and we can say interturn faults, right? That is also one of the incipient fault. So, and whenever you are having any oil expansion, low oil level, you can say, or change of oil properties, moisture entered into the oil, right? Moisture entered into oil, right? All these are the incipient faults, And second type of fault is internal faults, and third type of fault is external faults, outside of the transformer, right? See, for incipient fault protection, definitely we have to use Buchholz relay. For incipient fault protection, Buchholz relay we have to use. For internal fault protection, based on the rating, for small rating we can use Buchholz relay. For large rating we have to use percentage differential relay. That is called as merge price protection of transformer. For small internal faults or for small rated transformers less than 1 MVA transformers, so we can use Buchholz relay used for internal fault protection for small rated. For large rated, we can use percentage differential relay. But whenever there are external faults occurs, we can use overcurrent protection. The overcurrent protection will be given by which one? Fuses. So that fuse is going to give the protection from which type of fault? Fuse is giving external fault. It is not the low oil level. Low oil level is which one? That is incipient fault. That is given by the Buchholz relay, right? Thermal relays are used in where we are using the thermal relays. Motor starters, switchgear protection, transformer protection, and generators. So, generally the thermal relays are preferred in the motor starters, right? Because of severe overheat while starting, we have to use the thermal relays for motor starters, right? Overspeed protection of generator is done by overspeed protection of here they are giving options: governor, differential protection, overcurrent relays, and alarm. Any answer here? See, students, whenever speed increases, we know the induced EMF is always proportional to n into phi. For constant flux, whenever speed increases, the induced EMF increases, therefore the voltage level increases. So that because of this high voltage, insulation of the machine will be damaged. To avoid that, we have to use over voltage relay. But they have not given the over voltage relays in the option. Generally, for overspeed operation of the alternators, we have to use over voltage relays, but they have not given. But they have given one more part, that is the governor. Which is automatically correcting the speed. That is a speed governing system. The speed governing system, whatever the speed increased, that will be reducing. Whatever the speed reduced, that is going to be increased. That is an automatic action. Got it right, students? Very good. Right? So, if in the options, if you don't have governor, if you are having the over voltage relay, you can go for the over voltage operation. Right, students? Next one. The key job of the relay is to, what is the duty of the relay? Increase voltage, search the fault, reduce resistance, stop the current flow. Very good Balaji, very good, perfect answer. What is that? It is going to sense the fault. it is going to sense the fault. So, by searching, so it is going to sense the type of the fault, or not the type of the fault, searching the fault. That is the duty of the relay, right. A fuse operates due to dash effect of the electric current. A fuse operates due to the dash effect of electric current. Electrostatic effect, or heating effect, or magnetic effect, or chemical effect. Which one? It is heating effect. Very good. It is the heating effect. So, you can see, students, majorly the previous questions are consisting of fuse wire also. So, we need to discuss about the fuse wire also. So, means we have to concentrate on the fuse wire. Clear, right? Alright, students. Reverse power relays are used for protection of. Reverse power relays are used for protection of what? Any answer here? Reverse power relays are used for protection of generating stations, transmission stations, transformers, and domestic power supplies. So, almost everybody giving option A, very good. So, the reverse power relays are used for protection of the generating stations, right, students. So, actually, so whenever the generator supplies power to the grid, suppose this is the grid or infinite bus, right. So, in this direction active power is flowing, in this direction reactive power will be flowing. Suddenly, so initially mechanical input is existed, Ps is not is equivalent to 0. Whenever suddenly mechanical input failed, whenever Ps is equivalent to 0, the grid can supply power to the generator, so that the power is flowing in the reverse direction, right. So, this reverse power is trying to rotate the turbine which is coupled to the generator in the reverse direction. So, because of that rotation, the turbine blades may be damaged, but actually thinking turbine inertia is very high. How a generator can rotate the turbine is not possible. Suppose if it is doing that, turbine will be damaged, but the machine does not know it cannot rotate the turbine. To do that, it will take huge amount of current from the infinite bus, due to which the transmission system will be damaged, right. If the transmission system is not damaging, what happens? The turbine blades will be damaged, anything. That is why, to avoid that damage, we have to use a relay, so which does not allow the power in the reverse direction, that is called as the reverse power relay. Reverse power relay, or it is also called as watt metric relay. Reverse power relay or watt metric relay, right, students? Right. The fusing factor. So, what is the fusing factor? Fusing factor. Fusing current. Fusing current divided by normal rated current. Normal rated current. That is the definition of the fusing current, fusing factor. Students, actually fusing current, the current at which fuse will be melted and will be opening the circuit breaker, opening the line. Normal current means the highest amount of current that is flowing through the fuse wire without melting, right. So, at rated current, the fuse is not going to be melted. At fusing current, the fuse will be melted. Definitely, the fusing current is more than that of the rated current. It is always greater than 1, and its value approximately is equivalent to 1.45. 1.45. The fusing current is always more than that of the normal rated current. Right, students? These are the questions we are having. So, from the power systems part, still there are lot of topics to discuss, right. For revision series, that much time is not sufficient here. So, we have to concentrate on the remaining subjects also, students. So, try to prepare all the topics, do not leave any topic. So, as I have told you, so what to practice means which questions you have to practice. Previous RRB JE, SSC JE, previous ESC questions, GATE questions, and some state board questions also you can practice. Students, we are giving 30% discount for SSC JE and RRB JE and all state examinations. So, in 8th and 9th of April 2025, and use this code SCS30. Right, students? That's all for today's session. If you are having any doubts, please clarify doubts. If you are having any doubts, please clarify doubts. Yes, greater than only, given value is 1.45, not that much very high. Narmata, fusing current, just below it is not melted, just above it will be melted. That is why it is somewhat close to 1. Right. Please clarify doubts if you are having any. Right, students. So, that is all for today's session. All the best everybody.